Today we are going to see about step index and graded index fiber. Before going to that, fiber is made up of two materials. One is the core, the other one is the cladding. And these materials are based on their refractive index profile. Refractive index is the velocity of light in the particular medium divided by velocity of light in air. So when light travels from one medium to another medium, its velocity changes. So we have a small setup here to see that refraction. So I have a beaker full of water, which is one medium, and the surrounding air as the another medium. Okay, so when this light falls into this, travels from one medium to another medium, its path changes or some kind of bending can be observed. Actually, above the water, that is in air medium, it is in another orientation, and when it is dipped in air, we can clearly notice there is some bending. This phenomena is called refraction. This refraction depends on angle of incidence. So when the angle changes, the refraction changes. So how to minimize this refraction or how to nullify this refraction is by changing the angle. If the incident angle is 0, there is no refraction. Okay. Now we move into the concept further. That is, when the incident angle is below a critical angle, it crosses the medium and enters into the new medium. Right? This is refraction, the normal phenomenon. But for a certain angle, which is called as critical angle, the ray follows the intercept between the both medium. That is, the refracted angle is 90 degree. That is, it is not in the air medium or not in the water medium, right? So this is a particular angle, critical angle. And above this critical angle, what happens is, the light ray enters into the medium and it is reflected in the medium. What we generally expect is the refraction, but here, since the angle is above the critical angle, it is trapped inside the same medium. So let's have a small video to demonstrate this total internal reflection. Okay, some glass medium is placed, the outside medium is air, and we pass the light. We can clearly see for the 0 angle, there is no reflection or refraction. So once we increase the incident angle, the angle of refraction changes, and near that critical angle, the light ray goes through the interface of air and glass. Okay, we can clearly note this one, and beyond that one, it is completely total internal reflection. That is, by changing the incident light angle, we trap the light inside the same medium itself. This is the concept used in optical fiber communication and optical fibers, where we have very high speed internet and data communication thanks to this optical fiber technology, right? So it works on the principle of total internal reflection. That is, light will be falling into this fiber and it will be internally reflected. Even though there is a change in medium, there is one core, that is the inner medium, and there is cladding, outer medium. Even though we have two medium, the light will be trapped in the core alone. So the optical fibers are very lightweight, very thin, and they are very effective. So we can send this light as a signal into any long distance, and we can send more than one signal also. When sending more than one signal, we have one difficulty, that is the ray get mixed, the signal get mixed. They are of different colors, different wavelength, different frequency, and the core is having different material. So based on these things, they have some interaction among themselves so that the signal quality is slightly lost. This is called intermodal dispersion. This occurs only in multiple signal arrangement. If there is only one signal sent, there is no intermodal dispersion. But if you send more than one signal, this intermodal dispersion is there. There is an issue. So we need to solve that one. For that, what we have done is, so this is the normal fiber arrangement. That is, the inside is the core and outside is the cladding and the end is the protective layer. So in this case, if you send multiple signal, it is gets suffering that total intermodal dispersion. So in order to avoid that one, what we have done is, we keep the refractive index of the core as varying. At the middle, we keep the refractive index as maximum, and when it approaches the cladding, we keep on reducing the refractive index, so that at the core cladding interface, their refractive index is the same. Okay, so this is we classify that into two. So this is the normal one, that is called as step index fiber, where the intermodal dispersion is maximum. So again here, to eliminate that intermodal dispersion, we have reduced the refractive index gradually from the center of the fiber to the core cladding interface. This arrangement is called as graded index fiber. So we use Matlab to study this step index and graded index fibers. So I have loaded this step index and graded index data into the Matlab software, and we'll plot multiple graphs to understand this concept. So here we can clearly see, in this step index fiber, the refractive index changes suddenly, or I can say the refractive index changes step by step. Okay, for better understanding, I will plot a 2D graph. So here we can clearly see, so in the core and cladding, the refractive index is changing in stepwise. I'll go for 3D. We can clearly see, in this profile, there is some stepwise change in the refractive index, so that light will be trapped in the core alone. Okay, so this is the step index fiber. So there will be some core cladding interface. The refractive index changes suddenly. Okay. Now we will go to this graded index. When we plot the one-dimensional graph, you can see it's not stepwise here now. So from this one to this one, 2 to 8 is the core, and this is the cladding. In the original case, it is something like this, but here it is not like that. From the core center, it is changing gradually, and at the core cladding interface, it is almost the same. So we'll plot two-dimensional image. So we can clearly see some gradual change in the refractive index from the midpoint of the fiber, so that the total internal reflection phenomena happens in a different way, so that to eliminate the intermodal dispersion. In the 3D, we can clearly see, look at this arrangement. It is not the rectangular shape, it is a dome shape. It is clearly indicating the core and core refractive index is changing continuously. Now, what is the use? Now, what actually happens is, this is the core and cladding interface, this part. So, when a light enters into this area, it gets total internal reflection. Because there is refractive index of cladding is different, refractive index of core is higher. Now, in this graded index fiber, what happens is, in the next one, this is again core, but it acts as a cladding now. This is acting as a core because this is having a higher refractive index than this one. This layer is having higher refractive index than this lower layer. So once again one total internal reflection happens. Then in the next layer, the previous core now acts as a cladding because its refractive index is lesser than the next layer. So in each layer, wherever the light goes, it produces one total internal reflection. So unlike the conventional fiber, where only one total internal reflection happens, but here in between each layer, because it is graded, one refractive index is happening. So this is the specialty of this one. So this concept eliminates the intermodal dispersion. This is the step index fiber where the zigzag movement of total internal reflection happens. Only one total internal reflection from this entire area. But in the graded index fiber, in each layer, because it is varying refractive index profile, in each layer it is having one total internal reflection, so it bends. So instead of a zigzag path, the light ray has a helical path. So this happens when we send multiple signals. Here they go in zigzag, so they meet and they lose their signal. But in the graded index, what actually happens is, even though if we send multiple signals, they never overlap. So in graded index fiber, the intermodal dispersion is reduced very much. And we use this graded index fiber in multimode communication in a short range. For example, if you want to send the signal into a very long distance, we generally go for single mode step index fiber, which is having no intermodal dispersion. Thank you.